And during doing theory, it is very necessary to that we always encounter the numerical methods in physics. And I am sure that in the undergraduate level physics course, we have many numerical methods for solving some problems in the form of computational physics practicals. So, although this is a course or faculty development program in computational physics, we have to understand, we have to appreciate that computational physics does not always mean computer programming, teaching computer programming. As college teachers, you have to introduce the students with numerical methods of solving problems, which is part of your practicals of different papers like mathematical physics or classical mechanics or statistical mechanics or even quantum mechanics. So in this talk, I will train you. Of course, the time is very short, like 1.5 hours. We cannot cover most of the things in this 1.5 hour slot. But anyway, I will try to introduce some elementary methods of solving programs, so that if you know some language, computer language, or if you have access to some software packages in your laptop or in your desktop, so that you can implement these methods directly to solve the problems, and you can teach your students that okay, these are the methods, numerical methods of solving physical problems, and we can implement our numerical methods in computer packages or in computer language. And finally you can do your practicals, and you can make your students happy that you can solve physical problems in computer by using numerical methods. So first of all, I will introduce you what is numerical method and why it is necessary. Then I will go to some method of solutions of algebraic equation, of transcendental equations, as well as of certain techniques for integration and techniques for differentiations. So let us go forward. This is normally introductory remarks that you always encounter, or you should inform your students. Why do we apply numerical approaches to physics? Why it is adopted? So numerical approaches in physics are adopted in order to obtain either exact solution or approximate solution to some physical problems. We have many physical problems. As physicists, all of us know we have many physical problems which are complicated in nature. In order to find out the solution of the equations of the physical problems, we need some method of solving. And most of these numerical methods are used in the field of physics and astronomy, and we encounter the numerical methods in order to solve the problems of physics and astronomy. So when we apply numerical approach, the question is, when do we apply numerical approach? The only and only answer, if a complete solution is not available with us, if we do not know the complete solution of a physical problem through traditional mathematical tactics, then we apply numerical approaches. Okay, is this point clear to everyone?
Yes.
When do we apply numerical techniques? If it is clear, then I can move forward.
Yes, it's okay. Fine. You can move.
Yeah. So this is one issue that we normally address, that when a complete solution of a physical problem is not available through conventional mathematical technique, then we adopt the numerical technique. So what are the tools required in order to have numerical solution to physical problems? These are the tools. You need graphing software like Microsoft Excel, MATLAB, Mathematica, or whatever it is. It is your choice. There is no guiding line that you should have this kind of software to plot a graph. It is your choice that you install some software in your laptop. Then of course you have to know computer language, the programming language we call, and also you need very good computers so that you can solve it without any interruption. Any complicated tasks, physical problems you can solve by using these numerical techniques. So you can implement the methods that I am going to discuss in your computer in order to solve some interesting problems. So you can introduce your students in this way, that when do we need numerical approach? This is the situation we need numerical approach. When a complete solution is not available, through mathematical techniques available with us, then we take help of computers or we take help of numerical methods, and this is the necessity of doing numerical techniques. So what are physical problems? This is the second question. What do you mean by physical problems? Suppose your students ask you, what do you mean by physical problems? The physical problems are nothing but some mathematical equations. For example, Newton's laws, Maxwell's laws, the distribution of velocities of statistical particles. These are all physical problems. We always encounter equations of physical
Excuse me,
problems.
sir. Screen is not
Yes,
coming. Screen is not
screen is
coming.
screen not coming.
1 minute, 1 minute. Yes,
Flash are
someone
not
has
coming.
shared the screen. So I request all the participants, please stop sharing your screen. Then only it worked smoothly.
Yeah, 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 yeah.
Dr. Sanjeev Kalita, if you don't mind, please share again your screen so that
Correct,
the
correct.
everyone can see that. Or participant can do one thing that whenever some problem, you can rejoin the program. That
Yes,
problem
yes,
will be solved.
that will be better. Yeah. Can you see now?
Yes, you just
Okay.
make it a full screen, then it will
Yeah,
fine.
correct. Okay. So we were asking what are physical problems? Physical problems always appear in the form of certain mathematical equations. What kind of equations? These may be algebraic and these may be transcendental equations. Algebraic equation means you have polynomials in the left hand side and right hand side equal to 0. Transcendental equation means you have non-polynomials, for example, trigonometric functions or exponential functions, which algebraic functions together, and these are all complicated functions that we have. Then, of course, in physics, we always encounter ordinary differential equations and partial differential equations. I mean, for physicists, as a physics student, when BSc physics students are introduced to mathematical physics or any physics like classical mechanics or electrodynamics, always people will encounter ordinary differential equations and partial differential equations. So these are like part of life for a physicist, and we have to solve many complicated differential equations which boundary values or initial conditions given to us. So how do we do that with the help of computers? This is why we need numerical approaches. All solutions may not be available with us by analytical method. Okay. What is analytical method? If we have a closed form solution or if we have a well defined function coming as a solution of some equation, we call it as analytical solution. You can do it with pen and paper, but most of the physical problems always do not become simple. I will give some examples. In order to solve some complicated problems in physics, we need numerical approaches where solutions come in the form of numbers, discrete numbers. In analytical solution, your solution comes with the help of well-known functions, fx, some function which is known to you. But in case of numerical, we do some kind of discretizations. Instead of dealing with continuous functions, we deal with discrete numbers which come as a solution. So in numerical approach, we initially guess some solution of a particular equation. This is trial and error method, as people call it. We have some initial guess that okay, x naught is the solution of the equation fx equal to 0. Suppose x naught is the solution. It is an initial guess, but it is not the exact solution. The exact solution is somewhere else in the real line x axis. So what we do some numerical iterations, we do some numerical steps and run some steps. You can visualize it as a simulation you are doing in a computer. We run the solutions for many number of times, n number of times, so that we can arrive at the exact solution, suppose x1 or x2 or x3 or xn, starting with an initial guess x naught. So there are several steps which are required to arrive at the exact solution for obtaining the solution of the problem. Okay, these are differences between analytical and numerical solutions. So basic point is analytical form means you have a continuous function, well-known function coming as a solution to your equation. And numerical means these are approximate solutions which may come in the form of some numbers up to maybe n number of decimal places. It is up to you, up to how many decimal places you want your solutions. So always it is discretization in numerical method and it is continuation in analytical method in the form of continuous functions. Okay. So numerical approaches are adopted in various fields of physics. I am giving only few examples where you can tell your students, you can motivate your physics students. Otherwise, they will think that okay, This computational physics means something like programming and something like computer language, and they will forget all physics. Okay, so as a physicist, as a physics teacher, you have to introduce your students with some physical problems where you have to tell them that okay, these are some problems which we cannot solve by pen and paper. We need help of computer programs, we need help of computer softwares in order to have numerical solution to such physical problems. So one problem is the classical problem of central force or planetary motion. This is a very famous equation in physics. We know it as Kepler equation. You can open the book of Goldstein, Classical Mechanics by Goldstein. You will get all these examples where we don't have an analytical solution. So phi is the polar angle of a planet moving around a star, for example, sun. Earth is moving around sun, or any planet moving around sun. Phi is the polar angle, and E is the eccentricity of the orbit. We know it is elliptical orbit. And capital P that you are seeing on the right hand side, this is period of the orbit. And T is the time, and T perihelion is the time of occurrence of the perihelion point in the orbit. And phi naught is the initial position of the planet. Now, you see, this is a very complicated equation. This is something like x minus e sine x equal to some variable t. So what we have to do, we have to solve this equation phi as a function of t. All others are constant. Eccentricity will be given to you. Phi naught, initial position of the planet, is given to you. Period will be given to you. So in the problem, what you have to do, you have to solve phi as a function of t. And you can see this is horribly complicated equation because it is something like x minus sine x equal to t. And if you want to express x as a function of t, then algebraically you cannot do it, is it? Because it is a transcendental equation. The left hand side is not a polynomial, it is trigonometric function, and this is algebraic function mixed together, and the right hand side is the variable. You have to find phi as a function of t. So you have to introduce the physics problem in this way, that we cannot solve this equation. For example, Kepler equation we call in classical mechanics. This Kepler equation, from last 300 years, people have been trying to solve it analytically as well as numerically. But after advent of the supercomputers or the advent of the method of simulation or numerical methods, people now have a satisfactory solution of this equation. So people take help of this solution of Kepler equation in order to predict the position of planets and the solar system with respect to time. So this is very handy now. This is the importance. You can motivate your students that okay, this is a very important problem in physics. Now we want a solution phi as a function of t by the use of numerical methods. Then second example is when you have n number of particles. Okay, two body system you can easily solve in classical mechanics. You have come across the idea of reduced mass problem. So two body problem is very easy to handle. So if you increase the number of particles by one, it becomes three body problem. It becomes extremely complicated. And famous mathematicians like Poincaré have also tried to solve long back the three body problem after the advent of classical mechanics. But now we do it, we solve the three body equation of motion with the help of computers. N-body dynamics we always encounter in many physical problems. Gas molecules, motion of stars in an effective gravitational potential. For example, our galaxy, Milky Way, has n number of stars, billions of stars, moving together around the center of the galaxy in a common gravitational potential. Now, how to calculate the potential for n-body? How to calculate the orbits of n number of stars moving in the galaxy? It becomes a very complicated problem. We never handle with hand, with pen and paper. We do it by numerical techniques in computer. Okay, these are motivations for your students. You should take it when you go home. Then we have nonlinear problems in physics. For example, in dynamics, we have rocket motion. This is m naught is the initial mass of the rocket and the fuel inside the rocket. Uf is the final velocity of the rocket. T is your time. So what you have to do, you have to solve this equation to find out velocity of the rocket with respect to time. This is also very nonlinear equation because the u function is appearing under the exponential sign. So what we have to do, we have to find out the solution u as a function of time. But we see this is extremely non-algebraic equation. We cannot solve it simply by pen paper. Okay, of course you will do it with some very simple approximation. You can solve it by your hand with pen paper, but if you want complete solution exact the numerical solution, you have to take help of computers. So this is where computational physics comes. Okay, first of all, you have to formulate some physical problem, then you see whether you can find out analytical solution. If not, then you search next whether we can find numerical solutions. This is why I wanted to discuss numerical methods of solving physical problems. This is your for your students, that you have to introduce this subject in this way. These are only few examples where we apply numerical approaches. Of course, there are examples like chaotic behavior of a system, turbulence of a fluid. These are all extremely complicated processes, and I am sure that some experts will tell about this, how to apply these computational physics methods in order to solve physical problems like the chaos or turbulence, etc. So what is numerical method being? Numerical method is a bridge between pure theory and experiments. Why? Because when you do experiments, always your data will come in form of discrete numbers. Okay. For example, you are taking the simple harmonic motion problem. So what you do, you measure time period by some discrete number of experiments, say 5 number of experiments, 6 number of experiments, or 10 number of experiments you do. So you measure time period of oscillation in discrete number of data points. You never have a continuous functions in your experiment, right? So when we do some experiments, we have discrete data points with us in the form of some tables. And from these discrete data points, discrete numbers, we have to draw some inference that, okay, this is my theory. So numerical method is acting like a bridge between pure theory and experiment. I have given two examples over here. If I want to calculate velocity from the forced data, theory is this. This is Newton's second law. Do you agree? Velocity equal to 1 by m integration of the force over time. Okay. This is Newton's second law in integral form. Now what I ask, you ask your students, okay, I will give you some force data. Suppose I have done some experiments on mass m. I have applied force on this mass m 100 times. So I have 100 data points, f1, f2, f3, f4, f5, f99, then f100. So I have 100 data points for forces. From these 100 data points on forces, I have to calculate what will be the final velocity of the particle at any time t. Okay. So always in your experiments, you have discrete data points. In this case, you have force data points. From these discrete data points, you have to find out velocity. Now, how to do it? If you ask your student that I will give you some analytical function for force, they will immediately integrate it and find out the velocity as a function of time. That is called analytical solution. But in your actual experiments in physics, you don't have any analytical function, right? In your laboratory, you have only discrete data points for forces. Now, how to integrate discrete points? That is the main problem. Okay, we cannot integrate discrete data points to find out the velocity. So then we need something called numerical solutions for this particular equation. So this is a bridge between pure theory and experiment. Similarly, we have some elementary law called Newton's law of cooling in heat and thermodynamics, where temperature of a hot body cools down with respect to time in this form. So this is k is a constant. So definitely in your experiment, you will have time, you will measure it in a stopwatch. So these are discrete time points. You will measure temperature in a thermometer, which is also discrete data points. You have to finally integrate this equation and find out how temperature is decreasing with respect to time. So how do we integrate equations? How do we differentiate equations that is necessary in discrete experimental data? Then we need numerical methods. Okay. So if it is clear, then we go to the next phase. In physics, always we have the issue of integration. I call it as a hazard of integration, because every time you have to integrate some function, every time you have to solve some differential equations. So we call it is hazard of integrations. And life is not always simple. You will always encounter complicated problems. One very famous problem in physics that students encounter in BSc is the oscillation of a pendulum. Okay, if you ask this higher secondary student what is the time period of oscillation of a pendulum, he or she will immediately answer it is twice pi square root of L divided by G, where L is the length of the pendulum, G is the acceleration due to gravity, right? But this is actually an extremely complicated problem. The answer twice pi into square root of L by Z is valid only for small oscillation. Okay, this is why I am sure You college teachers always ask your higher secondary students not to oscillate the pendulum greater than 4 degree or 3 degree. Am I correct? Okay. If you are hearing, then you can realize then this is a problem that we encounter for oscillation of a pendulum. So what we do is that if the oscillation angle is not very small, it is very large, then the time period of oscillation of a pendulum is actually a very complicated function. This is integration from 0 to pi by 2, 1 minus a square sine square phi, whole thing to the power minus half, then integration over phi, where a is related to amplitude. I don't say exactly amplitude of the oscillation, it is related to amplitude of the oscillation. So this is constant. And this integration, now if you show your students integrate this function 1 minus a square sine square x whole thing to the power minus half dx, if you ask the students to integrate this equation, they will not get the answer. This is an extremely complicated integration. We call it as elliptic integrals. In physics, these integrations are called elliptic integrals. We have to learn some method of integrating these kind of complicated functions, so that in case of oscillation of a pendulum, I can actually calculate the time period of oscillation capital T. Now you can easily see that suppose your amplitude is very very small, so a square is negligible compared to unity, then this function become 1, and an integration of the phi will become pi by 2, then your student will get the answer twice pi square root of L by z. But this is an approximation. If your amplitude is not very small, then this approximation will not be valid, and this complicated function you have to take into account. So you have to learn some numerical integration method. If your function is extremely complicated and your data points are discretely given to you for the oscillation angle phi, then you have to learn the method of numerical integration, so that you can have approximate answer to the time period capital T. Okay, so these are situations where we encounter numerical methods. Okay, then let us explore some methods of solving and integrating. Okay, if it is algebraic or transcendental equation, we call solving. If it is differential equations appearing, then we call it as integrating. Okay, let us take some equation. This is fx equal to 0. This is some equations we have taken. Fx equal to 0, where fx may be a polynomial, then we call it as algebraic equation. If fx is non-polynomial, we call it as transcendental equation. Okay, non-polynomial in the sense fx you cannot express in the form of normal polynomial like x to the power n plus x to the power n minus 1 and so on. Okay, now how to solve this equation? Fx may be anything. I will give some examples. Now suppose x naught is the initial guess. I told you that in numerical solution you have to have a initial guess root. So let us assume that x naught is the initial trial and error root for this equation. So by first order Taylor expansion, we can have the next guess is x1. Suppose the next guess is x1. It is called first order iteration or first step. Ex naught is initial guess. So fx1, if x1 is very close to x naught, then you can have a Taylor expansion, first order Taylor expansion like fx naught plus derivative of f at x naught into x1 minus x naught. So this is known to everyone. A student will know what is Taylor expansion, first order Taylor expansion. Now suppose x1 is the desired root of this equation. Okay, then we can write fx1 should be 0, nearly 0. If x1 is the desired root, fx1 will be 0. Then we can easily work out then x1 will be equal to x naught minus fx naught divided by derivative of f at x naught. So this, if it is your x1 is the exact root, then stop it here. Otherwise, what you do, in order to achieve the actual root, which you have to go for nth number of iterations. So what you do, then you find x2, you find x3. So I am writing xn plus 1 is equal to xn minus f xn divided by f prime xn. Assuming that you are approaching the exact root in nth iteration or nth step of your calculation, we call iterations, then xn plus 1 may be your exact root of this particular equation. Okay, so this method of iteration from an initial guess x naught is known as Newton-Raphson method. Hello.
Oh,
Hello, Dr. Sanjay Kalita. Are you there? Hello, Dr. Sanjay Kalita. Are you there? Can you hear me? Slide. Slide जो है ना. Dr. Sanjay Kalita, we cannot hear you. Can you hear us? Dr. Sanjay Kalita, we cannot hear you. Dear participant, please wait for some times. Maybe some problems is facing by our resource person. Hello. Oi. Dear participant, I'm very sorry to inform you that our resource person, Dr. Sanjeev Kalita, has some emergency. So he has to leave for this session. He will not able to deliver this session. So I'm very sorry. We'll try to manage in some other time slot to repeat this session. So we cancel this session for this time. So we'll resume our next session at around 11:45 p.m. I'm very sorry. Dear participant, hope you understand. Our resource person, Dr. Sanjeev Kalita, has some emergency. So he has to leave from this session. So we'll try to manage these sessions once again in some other time slot, if possible. So our next session will start at around 11:45 a.m. If you have any query regarding this FDP, then you can discuss here. I have already shared the recording session of yesterday. I think you all received my mail with this recording session. And one more information is that on the last day, on 9 January 2021, we'll take a MCQ test on Python, where it will be for 1.5 hours, around 50 MCQ question. And we decided to provide the certificate of appreciation with grade for that FDP program, MCQ test. And we'll select 3 high scorer participants, and we'll separately provide them certificate for their excellency. So participant, you have any query regarding this FDP or any suggestion so that we can conduct this program smoothly? If you have some requirement, then you can inform us. We try our best to cover all the syllabus as far as possible. We requested our resource person to cover as many as possible syllabus under UG course. And if you have any particular requirement in any section or any topics, then you just please inform us so that we can arrange. If possible, we'll definitely arrange. You can write to our mail also. You have any query, dear participants, freely discuss, because this is now free time for us.
Can you just repeat the good morning? Can you just repeat the last lines? I missed. You were talking about something about the certificates.
Which one, madam? I didn't get, madam. Please repeat it once more.
You had just said something about the certificates. I missed that
Okay,
because my connection was, yeah.
We'll definitely provide e-certificate for your participation for this course. And one more thing is that we'll provide the one more certificate for your MCQ test with grade. Means we'll take one MCQ test on Python on the last day, 9 January 2021. If you see the program details, then you can see this MCQ test will be for 1.5 hours, around 50 MCQ question, and we'll provide a separate certificate for that exam, and we'll select 3 excellent participants who score highest scoring, and we'll provide certificate of excellency for that also, madam. Is it clear, madam?
It is clear. Thank you so much. And it will be an online test?
Yes, online MCQ test.
Okay, thank you so much. Thank you.
Okay, welcome, madam, welcome. Any more query from the participant side? As I said,
good morning, sir.
Yes.
So we will be having 2 separate certificates. One for
yes,
MCQ,
one for participant certificate will get.
Yeah.
And one more for if you appear or attend the MCQ test. And one more certificate if you score highest mark.
Excellency,
yes,
certificate of excellence.
Excellency will provide first and third position.
Okay.
And
okay.
That will be only on Python theory based.
Okay. And for this hand-on session, no sir, hand-on tutorial session.
Yes,
is it possible? Is it possible that we are provided the material earlier? Like before the hand-on session, if they provide us the material, then
our resource person, Dr. Nerit Borkogdi, because he is mostly taking this Python session. So I have requested him to provide us those material, slide or whatever. Then I will share with you all.
Okay, sir.
1 second, please.
Okay, sir.
Okay, participant, welcome back. If you have any query, then please inform us your suggestion, your comment. We wish your comment, suggestion on the feedback for this FDP program so that we can fulfill your requirement. We'll try our best. In the next section, to have very interesting also, that is also some introduction to computational physics with reference to the UG level physics syllabus. It will deliver by Dr. M.P. Bora, Professor of Physics, Guwahati University. He is very dynamic and excellent in the computational physics. I hope that this session will be benefited you. I wish your active cooperation for the session. মাকৰ বোলে এক্সিডেণ্ট হৈছে ইমান তেনেকুৱা নহয় অলপ কমকৈ এক্সিডেণ্ট হৈছে সেইকাৰণে সি কৈছে মই হস্পিটেলত যাব লগা আছে তাৰমানে মাজতে ফোন কৰিলে ন এক্সিডেণ্ট কিবা কাৰ লগত এনেকুৱা ধৰণৰ ইমান চিৰিয়াছ নহয় বুলি কৈছে এতিয়া গম পালো আৰু
স্যার স্যার মানে আমি ষ্টুডেণ্টখিনিক পাইথনৰ কাৰণে কোনটো ছফ্টৱেৰ ইউজ কৰিব দিম সেইটো অকণমান মোৰ কুৱেৰি আছিলে
অ'কে তাৰমানে যিহেতু যদি চিলেবাছ চাই বেলেগ বেলেগ ইউনিভাৰ্চিটিৰ মতে বা UGCৰ চিলেবাছ যদি চাই বা গুৱাহাটী ইউনিভাৰ্চিটিৰ চিলেবাছ যদি চাই then you will see that there are number of the software they have listed Python, Scilab, MATLAB.
Basically nthot canopy I guess
Yes,
isn't it yes
yes.
sir so we did the hands-on session on Jupyter Notebook and Google Colab. Should we suggest them to do the all practicals in that particular page, or we should suggest the nthot canopy? I am getting confusion regarding
Okay,
this.
it's better if you ask to our resource person, Dr. Nerit
Yeah.
Borkoteki. Okay,
Yes.
here's in this afternoon session, so you can raise your questions in that session. Okay, I think he will answer better.
Yes, sir.
Yes, Pratiksha Besbarua, madam, please.
Sir, actually, I had an interaction with Noedik sir on Sunday. So what I was trying to install Python in my Windows system, but I faced certain problem because my Windows is Windows 7 and it is a cracked version. So in the cracked version, I have been told that since certain updates the Windows is not taking up, so we shall not be able to install Python in the Windows cracked version. In some of the cases, it will not work. So from student perspective, if we see, they all of them might not be familiar or very much comfortable in Linux operating system. So if we can make them work in a Google Colab, I believe it would be better. I don't know what you suggest, madam. I think it would be better if they work it, but we can interact and we can ask Eric sir again about this. Maybe he can give us a better idea.
Thank you, madam, for your.
Ma'am,
Yes,
but ma'am, then we need network connection. That means without net we can't do this, no? So
technical question is stable or uninterrupted network মানে একটু লাগিব আৰু ক্লাউড হৈ ইন্টারনেট ইউসেজ তো অলপমান বেছি হয় বুলো অকমান
আৰু মানে ষ্টুডেন্ট খিনিতো এনেকুৱা কৰিব পাৰে অনলাইনতো কোডিং খিনি পাই যাব কপি পেষ্ট কৰি পৰীক্ষাটো দিলে that's why I was thinking কি এটো মানে কোনটো কৰিলে ভাল হ'ব ইয়াতে এটা সুবিধা আছে বস্তুখিনি কন্টিনিউয়েশন হৈ থাকে as a rough page we can do all this session but মানে এইটো ষ্টুডেন্ট খিনিক আমি কোনটো সাজেস্ট কৰিলে বেটাৰ হ'ব কাৰণ ইহঁতেতো একো নাজানে পাইথনটো একদম নিউ হয় সেইকাৰণে মানে ভাবিছিলো মই অকমান আমাৰ কলেজতো nthot canopy ইউজ কৰিছে মানে লাষ্ট ইয়াৰ আমি কৰিছো আৰু তো এইবাৰো চাগে ফাৰ্ষ্ট ইয়াৰ খিনি কৰা যাব বাট ছেকেণ্ড ইয়াৰ খিনিৰ কাৰণে প্ৰব্লেম হ'ব পাৰে নেকি নাম পাই আৰু ময়ো উবুণ্টু ইনষ্টল কৰোতে অকমান প্ৰব্লেম পাইছো কালি কৈ আছিলো ময়ো উবুণ্টু মানে লিনাক্স ইউজ কৰো সো সেইটো কাৰণে মানে অকমান ভাবিছিলো মানে আজি এবাৰ সুধিলে হ'ব মানে মই মানে এইটো ফাইলটো যেতিয়া মানে ৰান কৰিছো ন পিপটো মানে আপগ্ৰেড কৰিব দিছে আপগ্ৰেড কৰিলেও মানে সেইটোতকে বেছি আপগ্ৰেডেশন হোৱা নাই 8.1 লৈকে হৈছে সেইটো কাৰণে প্ৰব্লেম হৈছে চাগে
হয় হেতু হ'ব পাৰে নেকি হয়
আজি এবাৰ সুধিলে গম পোৱা যাব চাগে
মেবি তেখেতে আমাক ভালকে এটা আইডিয়া দিব পাৰিব হয় এইটো বিষয়ে
হেটো থ্যাংক ইউ ম্যাম
Thank you, madam. Thank you, sir.
Thank you all. Thank you for interaction. This is the platform of interaction, sharing our experience or knowledge, whatever. So I wish this kind of interaction from our participants.
Thank you, sir.
Welcome. If no more query, then we are resuming at 11:30 around. So our session will start at 11:45. So till then, I'm leaving from this room. So I request all of you please come back again at 11:30 a.m.
Sir,
Thank
link
you
will
all. Have a great day ahead.
link will be saved.
Accident এটা হৈছিল।
মেম লিংকটো সেমে চাগে 10টা পৰা
So,
এটালৈকে দিয়া আছে।
for the first session, for the morning session, the link will remain same, or you can check your bill. I have already shared. For the first session, means 10 to 1 p.m., the link will be remain same. For the second session, it will be changed.
Thank you. Thank you, sir. Thank you.
Okay, welcome, madam. Welcome you all. I hope all of you again join at 11:30 a.m. Thank you all. Have a great day ahead.
Hello? Hello, sir. Hello, hello. Hello.
Hello, Sanjeev.
Good morning, sir. Welcome.
Yes.
Sir, we are waiting for our participant. So we'll start at around 11:45 a.m. positively, sir.
Yeah, that's fine. Yeah, that's fine.
Okay. Sir, can you share your screen so that we can see whether it is working or not? It's fine, sir. It's coming, sir. We can see your screen, sir. It's fine. Good morning, everyone. Welcome back to our second session. I welcome you all again for this session. We have our resource person, Professor Madhurya Bora from Guwahati University. We welcome him. Dear participants, we have invited Professor Madhurya Bora for the session on the title Introduction to Computational Physics with reference to the UG level physics syllabus. And we are very much grateful to have the Professor Bora for this session. I'm hoping that this session will get benefited by our participant from his lecture. Before inviting him for presenting his lecture, I'd like to introduce Professor Bora with our participant. To do this honor, may I request Dr. Arundhati Mes, Associate Professor and Head of the Department of Mathematics from Bizra Mahavidyalaya, to introduce Professor Bora to our participant. Please, Madam.
Good morning to all. On behalf of Birchora Mahavidyalaya, I heartily welcome you all to the second day of the online faculty development program on undergraduate level computational physics practical using Python. With the introduction of CBCS at the undergraduate level, there have been a plethora of new topics that we must understand and in turn teach our students. So all of us need to upgrade our teaching skills. This program is a big step in this direction. Today, we are honored to have with us Dr. M.P. Bora, Professor of Physics in Guwahati University. He has a distinguished career, both as a scholar and as a teacher. He did his graduation from JB College, Jorhat, Assam in 1985. He then completed his master's and PhD from Delhi University. After this, he has worked as a research scientist in MIT, USA from 1996 to 1997. He was also a Commonwealth Scholar at the University of York, United Kingdom in 2013. He is the proud recipient of many awards starting from his school days, beginning with the NTSC scholarship in the year 1979. He has been awarded both with Junior Research Fellowship and Senior Research Fellowship from CSIR. He is the recipient of Boyce Cast Fellowship from DST in 1995, Best Thesis Award from the Astronomical Society of India 1996, Two-time Teacher Award from Jet Propulsion Lab NASA in 2006 and 2008 are also further laurels on his head. Commonwealth, he is also awarded the Commonwealth Academic Staff Fellowship in 2013. He has a number of papers to his credit and continues to excel in his profession of teaching and guiding research scholars in the present job at Guwahati University. May I now kindly request Professor M.P. Bora to take over and share his knowledge with all the participants of today's program. Thank you.
Thank you.
Thank you, Madam, for your nice introduction of our resource persons. Let us welcome the Professor Bora for this session. Welcome, sir.
Yeah, welcome. I hope you can see my screen. Yeah.
Yes,
So,
sir, we can see.
Yeah. So, first of all, thank you very much for introducing. That's very well. I'm not actually. I mean, it's not befitting. I'm like I do not deserve this much of this. very elaborate introduction. But nevertheless, what I want to say is that the UGCBSC syllabus in Guwahati University, and I was one of the architect of that whole system, and I'm still associated with the CBCS. In fact, all the queries come to me actually as a point of contact in CBCS. There are many things we devise, and many people are becoming, I mean, like they're very worried, like the skill section, the skill papers, and there are a lot of things which people do not know, and we continue to provide our services as a I mean, like modifying the interface, and then opening up some facilities to report any kind of inconsistencies in the syllabi. Recently, we have launched that in the SEC paper, no skill papers, so that anybody can go into that skill paper section of the syllabi portal of Guwahati University and report if you observe an inconsistencies. Then we look into it and then correct it quickly. So now, having said that, as you know that I'm sure that you have been already told about the CBCS syllabus, and in UGC recommendation is that we have to adopt whatever UGC has recommended over a a freedom of around 20% change in the different different subjects. But nevertheless, we must have now one thing is very particular in this, which makes it different from the present, the past syllabi, is that you have a experimental section in every paper, right from the first semester to the sixth semester. Every physics paper, I'm talking about the physics course, every physics paper has got an experimental section, and where you'll have to do the hands-on experiment either in laboratory or computationally. So they have given a lot of emphasis on computational because, for example, in the quantum mechanics paper, and if you want to do some experiment, then we cannot do anything in laboratory because these are very sophisticated instruments will require. For example, if I want to find out the, let us say, if I want to prove the uncertainty principle, it's not easy to do that in a PSC laboratory. So what they have resorted is that to do some numerical hands-on experiment. Now also that, well, this talk actually is supposed to be slotted earlier, but because of my engagements, I could not do this. So many things will be a very preliminary section. For example, when we have started digging up these experimental things, then we thought that how to do this because many colleges do not have the adequate infrastructures. As you can see that because this is almost 350 plus colleges under Guwahati University, it has to run, and it is running. And the college laboratories are, many colleges, there's a dismal condition. I'm not blaming the colleges, but given I mean, if you look at the fact of the day that the laboratories are not good, that's the experimental laboratory. But what about the computational? That's even worse, because sometimes all the department has is one desktop computer, and we don't know how to do that, how to carry out computational practical. Then we did a workshop, and we thought maybe we will introduce Python, because if you look at the Python part, it was not originally in the UGC syllabus. UGC syllabus doesn't have a Python part, but we have included in the Guwahati University categorically that it's either Python or any other language that you would like to, because Python provides you a comprehensive work environment so that you can take your environment with yourself. I mean, be it Windows, be it Linux, be it Apple Macs, be it many desktops, laptops, because many people are now having laptops. So we can tell the students to bring their laptop in and start doing Python. So it gives a one-stop solution, and that's why it should be encouraged. And nevertheless, so that's the whole theme. And now today, actually, what I'm going to discuss is not particularly any problem, but the caveats. That means the insight points of a computational physics. Because computational physics itself is a new topic for most of us, because many of our old generation people, I did computation, a lot of things, but many of the old generation people do not even have solved any numerical problem. Forget about the computational physics. So it will be very difficult for the teachers, some of the teachers, to tackle these problems with the students. And they not only have to learn it, but also they'll have to tell the students, teach the students. It will not be effective unless and otherwise you train them up. So this this actually FDP program is it's an effort toward that direction, and rightly taken up by Birjara Mahavidyalaya. And I do appreciate, and I must praise all the organizers for this nice event. And now, because it's online, so anybody can join in. And as I can see, the number of participants are increasing, 41 right now. And so you can actually get the benefit of all these things. But let us start without doing details. I think in 1 hour time, I'll be able to complete it and give us a view. And I'm not talking anything new, but everything, many people are already familiar with all these things. But nevertheless, I'll have to be as detailed as possible, because the strongest link of a chain is the weakest link. So if there are hundreds of teachers out of 41, suppose faculty members, if 10 faculty members do not understand that how the things go about, then it's meaningless. So we'll have to start from the very basics. Okay, so with that, let me start with that things. Now, I do a lot of computation myself. In fact, a lot of recent works are actually in computational physics. So the computation is now almost ubiquitous. I mean, like, you cannot avoid computation in any way. Let it be your research, let it be your writing papers, let it be your calculating graphs, and it is everywhere. So you cannot. So it is better to learn rather than to avoid these things. Now, yeah, I won't be wrong to say that the whole stuff of numerical analysis is to minimize errors. And the errors are actually, these are very simple, but let me just, for the sake of completion, let me tell that the errors which we actually have is, sometimes it is called round off error and it's called truncation error. I'm not going to give an example because everybody knows that. And round off error is actually the error which is inherent in a digital system, like a computer, like a mobile phone, like your desktop. It is inherent. You cannot shake off the round off error. Round off errors has to be there. We'll take some interesting example to see that how the errors actually creep up in your calculations. And a truncation error is, of course, it's specific to the algorithm. I mean, like if I'm finding a Taylor series expansion, then the expansion term that I cut off actually determines my truncation error. But nevertheless, round off error is always there. So basically, the numerical analysis is to how to minimize the error, because you cannot be completely exact in a computer. It's almost meaningless, because the computer have a very, very finite accuracy. Although it is very large, but the accuracy is finite. So it is meaningless to make the things like I can have infinite accuracy. It is no, you cannot achieve infinite accuracy. So the point is that you have to minimize the error. So you'll have to work on it. For example, let me take an example like, consider an integral. Let me just take this example for purpose. So this is a very, I mean, you can find this in Wikipedia. This is a very simple integral, and n is equal to 0, 1. I'm just giving an example of how the errors are playing havoc and how we can minimize things. Now, if you can solve this for, like, for example, if you solve it for n is equal to 0, then immediately you can find this is ln 6 by ln 5. No? Log of 6, natural logarithm, log of 6, and log of 5. Okay, and if you do n is equal to 1, then it will be 1 minus 5 ln 6 by ln 5. And if you do y2, then you can find is 9 by 2, then plus 25 ln 6 by ln 5, isn't it? So then y3 and so on and so forth. Now, if you look very closely, these relations, that you can see that y0, y1, y2, and y3, so on and so forth, they actually follow the recurrence relation. And if you look at the recurrence relation, you can very quickly see that what is the relation is. It is actually yn is 1 by n minus 5, n minus 1. So put n is equal to 0, n is equal to 1, then you get y0. Y0 is ln 6 by ln 5. You will get the y1 value. So this is a recurrence relation. Now the question is to calculate the yn using the recurrence relation. I mean, I'm not going to find out the integral as such. I use the recurrence relation to find out the integral and then do this out. Okay. Now, if my computer is accurate, completely infinite accuracy, I have complete control of the errors, then of course I don't have to bother about anything. I have y0, I can put it in recurrence relation that you can see on your right, right to the yellow big arrow. Then you can calculate 1. And once you can calculate 1, you can use that 1 to calculate y2, and y2 you can calculate y3, and so on and so forth. So you can just go on doing it, isn't it? But let us now try to see an hypothetical case that while estimating y naught, I have a very small amount of error that is called epsilon. Okay, I have a very small amount of admixture. The epsilon can be very, very small, 10 to the minus 6, 10 to the minus 10, or whatever it is. You can take about a very small number to the initial y naught. So that means I've added, deliberately, I have added an error. Now you can see that this error can be thought to be generated out of computation, because the computer ln6 by ln5 is not completely accurate. It will have some kind of errors, and that error is actually given as an epsilon. Now, if you plug in back the recurrence relation, you will see that in next step, the error becomes minus 5e. Not much, but it's 5e. You go once more step, then it becomes 5 square e. Go one more step, it becomes 5 QE. Now remember that you have gone up to 10. Then what will be the error? 5 into 5 to the power 10. And that will be enormously large number. 5 to the power 10, can you imagine how it will be, how big it will be? So it will be so big that the value of y will be completely off the track. It will be completely wrong, and you will end up a very, very wrong result. So even if your y is, now even if now you can see that if epsilon is suppose 10 to the minus 6, then 5 into 10 to the power 10 multiplied what amount of error that you will have. So this method is a completely unstable method. Now the question here is that if I have an error epsilon, which is inherent in the computation process, so I cannot avoid error. I can never make epsilon to be 0. It's not possible. I can minimize by increasing the bit size of the computer. Let us say 8-bit, 16-bit, 32-bit. Now it is 64-bit computers. So 64-bit computer, it will be very, very small, but nevertheless, it is there. Even if you make a 128-bit or 264-bit computers, it will be there. So the epsilon, you can never make it 0. That means what? I'll have to live my life all these errors. You'll have to ask yourself a question. Yes, you have to live with these errors. Then the question of numerical analysis comes, then how to minimize the error, or how to keep this error constant. So if instead of using this recurrence relation, if I can find a way to keep the error at one constant value, then my purpose will be solved. Okay, so this actually was the caveats. This is the art of computer programming, or computational physics, or computational methods, or numerical analysis. As you can say, this is the art of scientific computing. So this is actually rightly said by numerical recipes author W. Price. You know that book, Numerical Recipes, is a famous book. The title of the book is Art of Scientific Computing. Okay, so scientific computing is actually an art. Now let us consider, given one more very simple example, our good old quadratic equation. Ax squared plus bx plus c is equal to 0. Now many of you know that this is a very simple equation that you know in class 7, 8, or even 6. And we know the solution is simple. The x is equal to minus b plus minus b squared minus 4ac by twice a. Now, suppose I would like to calculate this equation, the solution, for a case where a and c are both very, very small compared to b. Okay, remember the case. Now a and c are very small compared to b. Now in that case, what will happen? The b square minus 4ac will be almost very close to b. Suppose ac of the order of 10 to the minus 10. Then b is suppose of the order of 1. Then 1 minus 10 to the minus 20 will be very, very nearly equal to 1, isn't it? Suppose b is equal to 1 and a is 10 to the minus 10, c is 10 to the minus 10. So b square minus 4ac will be 1 minus 4 into 10 to the minus 20, which is almost equal to 1, negligibly equal to 1. Now, if I take a square root of that and then subtract it from the one another, because remember you have a plus minus sign. So whenever you have a plus sign, you are subtracting two nearly very small numbers. This will necessarily require subtracting two nearly equal numbers. The addition is not a problem. The subtraction is a problem because you are subtracting two nearly equal numbers, and because they're very close together and the computer is not very accurate at that level, 10 to the minus 20, that means your answers will be wrong. So then the question is that how should I solve this equation? Should I not solve, or is there a better way? The problem is that I cannot eliminate my errors completely. That's a problem. The solution is that I have to modify my method in such a way to avoid subtracting. As you can see, that the basic point is that it nearly requires subtracting two nearly equal numbers. That means I have to avoid the subtraction. How do I do that? If you slightly manipulate your results, then you arrive at this answer. So what is the solution? The solution is this. So trick is to convert the plus minus sign to a plus sign. How? That's what you do. Compute the quantity q. As you can see, the sign before the square root is always plus, and this two quantity will be always additive. Because suppose b is negative, then SZ and b is sine of b. That means if b is negative, sine of b will be -1. That means both will be added together because both are negative. If b is positive, then sine of b also will be +1 positive, so it will be added together. That means this relation doesn't involve any subtraction of two nearly equal quantity. Now, once you find out q, then you can find out the roots as x1 is equal to q by a and x2 is equal to c by q. You can try, you can find. Okay, so that's a trick. So you have tricked the computer system so as to avoid subtracting two nearly large equal number. So that's a trick that we have to play. And you have to tell these things into the students so as to, it's not simply just brute force. I mean, our example, Pastor Loom, we will take an example that it's not like a brute force that you do something and suddenly, I mean, whatever is given as a formula, you are going to calculate it just like given in the exam, just like given in the textbook. No, it's not like this. You have to trick the methods in such a way to live with the errors, but at the same time, you get the required results. So it's like a coronavirus, you know. So we have to live with the coronavirus, but at the same time, we have to do our jobs. For example, this FDP is being conducted online. 1 year back, we would have never imagined that this would happen in all classes and schools and colleges. But now it's a norm of the day. It is so normal to have an online FDP that because there is a coronavirus, but we are still finding a way to do that. So that's what you have to do. And that's a numerical analysis is all about. Okay. Now we'll how to minimize error. Going by this, let us now try to, you know, sometimes finding an efficient numerical method is nothing short of a black magic. I mean, I have not said this. I mean, this is actually W. Price, the author of a numerical recipe, is actually written that sometimes finding an efficient numerical method is nothing short of a black magic. It's like as if I find something, you know, out of the box and I don't know where it's coming from. So, I mean, like it is something like, you know, you find a magic Aladdin carpet, you know, you find a magic lamp. And, you know, this is a famous scene from the Aladdin, you know, and there's a genie and there's a lamp. So you need to find some kind of lamp there and to find that what you have, what you devise a method. For example, let me take a very simple example, like a black magic kind of things. Consider this is a curve. Now that curve has got 3 points, as you can see, A, B, and C. Sanjeev, it is okay. Everybody is listening fine?
Yes, sir.
Yes, okay, sir.
Okay. Everything is visible.
Yes,
Okay.
sir. Yes, sir. Yes, sir.
Okay. Thank you very much. Yeah. Thank you, Pratik and Archana. They say it. Okay. So ABC is the 3 points, and I want to find out. I mean, I'm telling our esteemed faculty members so that they can pass on the message to our students, because you have to actually rise in the interest among the students. Otherwise, numerical analysis is pretty boring, and people tend to actually muck up and memorize programs, which is like a havoc. You cannot memorize a program. That's strictly no. So I have a ABC 3 points, and I want to calculate the differential df dx, and the curve is in f actually. The curve, which is denoted the black thick line, is the fx, and I want to find out the derivative at fx at x equal to b. Now, how to do it? If by analytically, I know that I have to take two nearly equal values of f around b, then divide by the distance between these 2 points, and the limit that distance goes to 0, then I get a derivative. But in the computer, I cannot take limit 0. That is completely impossible, because it will give a floating point error. So I'll have to take something called a forward difference. So fc minus fb, c minus b. And provided c minus b is small enough, I can assume that my errors are small. But if you say that this is forward difference, I can find out the difference, derivative value at b from forward difference, that will, from considering the forward point c, then I can also do the backward point c. I mean, that's also equally okay. So that means both the value should be similar. But as you can see from the curve, they are not similar, because the slope from A to B is slightly less than slope from B to C. So the forward difference that you find will be having errors which is different than the backward difference error you have. In fact, the error in the forward difference will be more than error in the backward difference in this particular place. Now the question is that how can I minimize my error? Okay, the answer is the central difference. That means I will take FC, I will take FA, then divide by C minus A. The errors here and errors here will get cancelled. Actually, you can check it by yourself. So here, your intuition doesn't work. Your intuition say that the difference between the point should be small. So C minus B is now smaller than C minus A, but still I'm getting a correct result, more accurate result. So that's the art. Your C minus B difference or B minus A difference, both differences are smaller than the difference between C and A. But even if you take a central difference, FC minus FA by C minus A, you will arrive at a slightly more accurate result than both forward and a backward difference. So that's the art. That's where you do. Okay, this is how you'll have to test the methods. So we will go on and slightly try to see. And so that's a minimum error, you can see that. Okay, so let's now try to go by your syllabi. Let us see. Now you have a syllabus. As you can see that you have, most of you can download the syllabus from our portal if you have not done. But you know that if you look from, somebody is switching on the microphone. Okay.
Sir, excuse me, sir.
Yeah.
Actually, I could not.
Yeah, tell me.
Actually, I could not resist myself. When you talk about FC minus FA, we are talking about 2 points which are at far distance. So, if we take the slope, if we consider the slope, it will resemble a straight line. So, will not be violating the curve pattern of that actual case.
Let me go to the these things. Okay. Yes. I mean, like that is what your intuition says. But if you calculate the value, you will get a minimum error. That's what I say. Even B and A also, you are taking only a straight line. You are not calculating the curvature. When you take the forward difference, even if that also is a straight line, you are taking the straight line difference only. But the thing is that when you take a central difference, you can work it out yourself. In this particular case, of course, I'm not saying that it's a universal thing, but this is one case where you will get a central difference error is minimum than the forward and backward difference. So what I mean to emphasize is that it depends on different methods. That means there is no single key for all the locks.
Okay, sir.
You have to divide different methods for different it comes from intuition actually, or intuition or experience, for example. Okay.
Okay, sir. Thank you, sir.
Now let us now talk about your syllabi. Now, if you go by the syllabus, then you'll see that all the experiments that you do from first to sixth semester, let it be the first semester methods, first semester paper and sixth semester papers, then you will find that all this matter, almost 90% of the problems that you encounter during a 3-year undergrad course falls into the following categories: solution of ordinary differential equation, numerical integration, solution of algebraic equations. Algebraic equation means you can have a polynomial as well as you have a transcendental equation. The interpolation and solution of partial differential equation. There are many other things also, like sorting, like first Fourier transformation, about which I'm going to talk about a little thing. And then you have got a image processing. All the things are there. But what I'm telling is that 90% of the textbook problems that you encounter in a quantum mechanics syllabus or a classical mechanics syllabus or electrodynamics syllabus actually falls into this category. So you'll have to master this art of those things. Okay. Now, I'm not going to solve problem for you, because already teachers or resource persons are there to do it for you, like theory talks are there. My job is to give an overall view, being an architect of the whole syllabus at the beginning. We have a core team at the ZU, which actually device. We sit once in a month and discuss all the problem. So let me tell you that how one should approach, because I have a long experience of around 28 years now by doing the computation, 28 years in Guwahati University, then 5 years my PhD, almost 30 years. So I have been doing computation. So I mean, like that, from that experience, what I'm going to tell you is that how should proceed. What idea you should have in your mind while trying to solve a problem. It's not that you get a problem and just you jump on the bandwagon. I've got a quadratic equation. I just use x is equal to minus b plus minus b square minus 4ac by twice. No, that's not the way to do it. You'll have to go by the real real art of doing it things. Okay, now let us try to solve and analyze a simple harmonic oscillator problem. I'm telling you how, by improving small things, how you can greatly improve in errors, how you can greatly minimize errors. That's what I'm going to talk about. Okay, now let us say this is a block which is sitting on a frictionless surface. It's a slightly blue colored block sitting on a slightly dark colored frictionless surface, and I have attached a spring which is attached to a rigid wall on the right. Can you recognize the picture? This is like a box of mass m, and it is connected to a ideal spring. That means the spring doesn't have any weight, and it is connected to a rigid wall, and then it is actually resting horizontally on a frictionless surface. Okay, and the equilibrium position is x naught. Now, if I want to now write down the equation of motion for this, immediately it's a simple harmonic oscillator equation, and in a nutshell, this equation can be written like this. Now you can see that I don't have any m, I don't have any omega. You'll ask me why. Where is the omega? Where is the m? So I said I have normalized this actually. I have taken m is equal to 1. I have taken omega is equal to 1. That means basically this equation can be written in a very naked form, like d2x dt square is equal to minus x. In actual form, actually m d2x dt square is equal to minus kx. Okay, so k by m I have taken as a 1. Okay, so that's what it is. Now this equation, if I want to solve it, I can also write down this equation in a slightly different way. The dx dt is equal to v and dv dt is equal to minus x. Now let us solve these two equations. And I know you are all familiar with solving this equation. I don't have to talk about the algorithm. I don't have to talk about the physics of it. I don't have to talk about the mathematics of it. You are all familiar with it because you are all esteemed faculty members and you know how to do that. You have been doing it. So I will use the Euler's method, which is very, very basic, and students also will like to use that. And you can solve this equation using Euler's methods. Okay. I hope everybody's familiar with the Euler method. I'm straightforward going to the mathematical formula for doing it. Okay. Now let us try to solve that. Now that's the Euler's method. Now in Euler's method, actually, what you do, you divide, you write in a discrete form. So I'm not going to actually explain all these things, but you know that how this is actually Taylor expansion of the first order. If you take x delta minus x t plus delta t denotes the x at a time t plus delta t. Xt denotes the position at x at time t is equal to t. Similarly, v at t means v at time t is equal to t, and t plus delta t means the time v sub t plus delta t means that v at time t plus delta t. Now, if you can see that xt plus delta t minus xt divided by del t, which is nothing but actually dx dt, is equal to v, that you can actually already see that we have already have that dx dt is equal to v, the first equation, right? And this is the first equation, and I have similarly vt plus delta t vt minus x delta, that's the second equation. Now let's try to calculate this equation and with the initial condition. Now, what is the initial condition? Because it's a simple harmonic oscillator, you cannot have x0 and v0 at the same time because they will be equilibrium. So if suppose at time t is equal to 0, both position x is equal to 0 and position v is equal to 0, then it will not move at all. So my equilibrium, my initial condition has to be that either at some displacement. That means if I can take that x is equal to 0, v is maximum. I can use that. That x is equal to 0, v is the maximum. And I can normalize vmax to something like 0, and this is like delta t. So time interval, I'm taking a very modest time interval 0.01, and x0, x is equal to 0, vmax is equal to v0 is equal to 1. Okay, so that's the initial condition, that initial point x0, v0, that means whenever x is equal to 0, v0 will be 1. At time t is equal to 0, the subscript denotes the time flag, and delta t, the interval of time, is 0.01. Suppose I try to solve this equation. Let us calculate a few steps. Okay, let us calculate a few steps. So this is my equation. Xt plus delta t is equal to xt plus vt delta t. Vt plus delta t is equal to vt minus xt delta t. That's a basic Euler's equation, Euler's method. Now let us do step 1. Step 1, x01, because remember our delta t is 0.01. That is first value I find at x is equal to 0.01. Now you can put a value, you can use your calculator or a computer. You can find that the value x0 is equal to 0.01 and v01 is 1. And the error from the, what is the actually solution of the equation? Your x is equal to sine t and v is equal to cos of t. Okay, x is equal to sine t, v is equal to cos of t. So that's the solution. So if I find out cos of t and sine of t and take the absolute error, that means deviation from the computational value, that is 0, 1 and 1 from the actual value, then I will find my error is 1.6610 to the minus 7 for x, and for v it is 4.99 into 10 to the minus 5 approximately. Now let us go to step 2. I mean, I'm not writing the full numbers because I cannot write the full numbers, but you can calculate it. X02 becomes 0.02 from this above equation, and V02 is 0.9999. And the error have slightly increased. As you can see that the error in now second stage is slightly more than the previous one. It's 1.32 10 to the minus 6 and 9.99 10 to the minus 5. Go to step 3. My errors have further increased. My x03 is now 0.0199, v03 is 0.9997, and the errors are 0.0101 and 1.49 10 to the minus 4. That's error in x, that's error in v. Step 4, x04 0.0299 and v0.04 is equal to 0.9995, and my error is 0.0101 and 2.99 into 10 to the minus 4. My errors are constantly increasing, and I mean, like, or at a constant or constantly increasing. The equation is that given this very basic Euler's method, can I improve upon it by slightly changing something? Okay, let us now see that. Now these are the errors. I have highlighted this because I want you to focus on these numbers. Okay, now remember how the process goes. That I actually use the initial value xt and vt, then calculate xt plus del t, then calculate vt plus del t. And next step I use this previous value in the old one, in the new one, and so on and so forth. I go on. Now let us slightly change the second equation. Instead of xt, because I have calculated xt plus del t in the previous step, I will use this x plus del t into the xt in the second equation in the rightmost term. That means it goes like that. I have not made anything. I have simply changed the xt value from whatever I have calculated in the earlier one. Now, if I do make this small difference, you can see how greatly my results will improve now. You can see that. Let us calculate step 1 with this new algorithm. Obviously, the first step, I don't have any change. The values are same. The V01 is also same. The errors are also same. Step 2, I have a surprise. The X errors is same, but Y error is down to 10 to the minus 4 times from the earlier value. 10 to the minus 5, the error is 10 to the minus 9. Can you see that? If I go one step further, the errors are now even in X also. You can see how greatly errors are reduced in X and V. If you go to step 4, you have seen that. Okay, instead of 0101, you have 3.6 into 10 to the minus 5. Instead of 3 into 10 to the minus 4, you've got 1 into 10 to the minus 4. Just a simple substitution of the earlier value of X in this algorithm, I have greatly reduced my errors. And that's the art. That's the art of computation. And this is actually what is known as a modified Euler's method. Okay, so this is like an example one should give to the students, that how by changing a little bit, tweaking a little bit your things, you can actually, of course, I'm not saying that you just take a hit and trial and try hit this at this. All these things what I have told you has got a solid mathematical background. But here, of course, I don't have a time to prove everything. But interested students and faculty members can always go to the textbook and see why the errors are reduced. But the thing is that it's that small step that makes a huge difference in your long run. Okay. Now let us now. Yeah. Somebody.
Excuse me, sir.
Yeah.
Yes, sir. While reducing the error, are we not compromising at the values of X? Because I can see here at the step 3, earlier case, the value was 0.0199, but in the second case, it was become 0.0299. So it's a 100% increase in the value of X.
No. You don't compare the values here. You compare the errors.
Oh, that's what error is reducing, but the displacement is changing its value.
No. I am comparing to the theoretical value. So you are going more close to the theoretical value of X at 0.02. Don't go by this number, because there is a string of numbers here. It is not 0.02. It is 0.02 something else also, because I don't have place to write here. I have cut it down there.
Okay, understood. But in the step number 3, the value of X 0.03 is changing too much.
Yeah, changing too much. That's why it is going closer to that true value. You can see the errors. Errors indeed.
Okay.
Earlier case was 0.01. Now it is 2.49 10 to the minus 6.
Okay.
These errors are calculated by comparing the computational value to the actual analytical. That means sin t and cos t.
Okay.
So these are fine. It's clear. So the errors are not relative errors. The errors are actually true values of the error. So if I suppose without any error, if I calculate, then I have got these errors. Okay.
Okay, sir. Okay, sir.
Fine. So that's one. Now let us talk about, because these problems are you encounter day to day. So let us talk about numerical integration. Again and again, I'm telling you that I'm not going to teach you integration because you already know it. I just have to explain what idea you need to have in your mind while solving an integration. For example, if I want to integrate a to b fx dx, this is a curve, area under the curve. So a, b is the limit, and you just find out the area under the curve, and that's the integration. Now, if you find the area under the curve, as you know that we all know with trapezoidal methods, that you divide the whole area into stripes, rectangular stripes, which are like trapezoid, so on and so forth. So I've got the trapezoids, which are there, right? Now, if you consider one trapezoids, and of course, you see that the curve is being approximated by straight lines, as you can see that. We'll talk about that a little bit later. But now if you try to find out what is the area of the one of the trapezoid, then you'll find that the area of the trapezoid, actually, these are the FA, and this is FA plus H, So the area of the trapezoid is given by half H, FA plus H. This arrow, I have the slightly blackened trapezoid, which I have marked with arrow. The area is given by half H into FA plus FA. It's actually formula for a trapezoidal area, okay? Now, if you add up all this area, then you get the final answer, which is nothing but actually this one. A to B, fx dx, half H, FA plus FB, H, FA plus FA plus H, and FA plus N minus 1H, okay? So assuming that there are n divisions, okay, you can. So this is trapezoidal method. This is how we find the integration. Now the question is how to improve upon this. Suppose I give a brainstorming session to the students that this is what the trapezoidal method. Your job is to make this method more accurate. So students might come up with this, that okay, I'll divide more. I'll divide more finely. That may increase the number of n. Yeah, that's a solution. But the error will remain, because a curve, no matter how finely chop it, the curve will remain a curve and straight line will remain a straight line. You can never approximate the straight line with a curve, no matter how refined you are. That means the fundamental error that is inherent in the trapezoidal methods, which is actually approximating the curve with a straight line, remains there. So you cannot remove this fundamental lacuna of these trapezoidal methods. Okay, that's why if your integration length is very large, then trapezoidal method is almost useless, because how refined I can do. Of course, if I want to find out the integration between 0 and 1, that might be fine. But what about 0 and 100? How long I'm going to refine the strips? Maybe 10 to the minus 20, maybe 10 to the minus 30. How long? I mean, it'll use a huge computer time. It's actually useless in that way, if you think. From 0 to 1, it might be okay. But we not only find 0 to 1 limit integration, in many a time integration limits are very huge. Okay, and you'll have to do a lot of many times. So suppose one integral takes suppose you say that, okay, I will make my stripe so thin, like 10 to the minus 20. But suppose then you'll have to find 10 to the 20 numbers of integrals. Then it will take one second to do it. If you had one integral, it will be huge time. Okay. Now the question is that how to improve upon this. Now we attack on the basic lacuna of the trapezoidal method, that it actually, what is the shortcomings? That it actually approximate the curve with a straight line, as you can see that. The curve with a straight line. If I magnify, then you can see that this is the. So I have a straight line, but actually there is definitely a curve. So if I want to treat this fundamental flaw, which is in a trapezoidal method, then how will I do this? I'll approximate this straight line with a curve. So that means I will feed a curve on these 3 points like this. Then probably, even if this curve may not be the same as the one that was integrating, but the errors will be still less, lot less in fact. Okay, and if you do that, and that's what is known as what is the method? Is known as a Simpson rule. And many of you may not be aware of this fact, that how the Simpson rule come into effect. This is actually because of the interpolation between the 3 points. That's why in Simpson rule, you take 2 intervals at a time. So this is how you have to think, that the fundamental flaw of the method, I'm going to attack it and then improve upon it. Now it's a different matter. How will I find the curve? There are many ways of finding this. Find the approximate blue curve that is actually approximating the red curve in the integration region. There's many ways of doing. One of the fundamental way of doing it is the Lagrange interpolation methods. And if you do that, then it becomes a Simpson 1/3 rule. If you slightly change this, then you have the standard 3/5 rule and something like that. So on and so forth, you can go on, right? I hope I'm clear. I hope, although you know all these things, maybe I can make you think a little bit differently and a little bit insight into the problem. Because many times what happens that our teachers, including myself, when we approach a problem, we approach the problem from the practical point of view that, okay, I have to solve this. I'll have to get this program, write this program from here, memorize it, compile it, and solve it. But that's not what we are going to do. That's not what our motive should be. We'll have to tell the students, or you know, that's, I mean, that's one of the lacuna of Indian system. Excuse me for going away from my talk, but I don't. Actually, I could not resist my temptation of telling it that 70 years after independence, we are still stuck with numbers. 99.9%, 99.5%, 99.2%. If my son has scored 95% in class 12, then it's very, very bad. C or C should have scored almost 100. Why not 100? If 99.8%, if not 100. 95 is a very, very bad mark. But the thing is that why we are running after marks? Because we want memorization. We give marks on memory. We don't give marks on knowledge. We don't give marks on concepts. The concept doesn't make any sense in our education system. It's completely rotten. You can see that the present employment scheme of the college lecturers. You will be happy to know, or you'll be surprised to know, that the 5-year you do research, write a paper in an impact factor 5 journal, that mark is less than if you have an NCC certificates. Okay, sorry for telling me this, because we are all related, even if we are, because sometimes it makes me talk my meaningless, because I'm talking all these things, everything looks nonsense given the fact that the students are knocking up all these things and memorizing all these things. So it doesn't make any sense. So as long as we don't improve our education system, this kind of talks are actually meaningless. So, but even if it is meaningless, I'm going to talk about it because you have invited me, and I will be failing in my duty if I don't tell you all these things. I take this opportunity to tell you. Actually, lately, I have stopped going to interview. I have refused too many times. I said, no, I'm not going to take an interview. Hire somebody else. It's not my job. It's not my cup of tea. Just sit there and calculate marks. Yeah. Okay, Lavita, thank you. I mean, like, many people will appreciate, but we have to boycott this system somewhere. Somewhere we'll have to come up and do some kind of rising that, well, we have to live for that, because we are teachers. We are teachers, and we are the persons who are shaping this future. And by using this kind of mucking up methodology, we are destroying the future of our students. Okay, so but nevertheless, let us go back. Let us go further, because otherwise I will not be finishing my talk. But I take this opportunity of telling you things. I hope you will do appreciate that. But let us see that. What else? Let us take the example of Fourier transformation. Now let us give me an example how how a simple realization gives rise to life-changing ideas. I mean, life-changing calculation. It's so life-changing that it is now back of all the calculation bone. So it is something like as simple as finding out the Maxwell's equation. Maxwell's equation, the backbone of our electrodynamics. No matter whatever you do, Maxwell's equation remains the same all the time. Okay, so this is what actually revolutionized long back by Cooley and Taki. Taki is a numerical analyst. Let us talk about the Fourier transformation. So all know that this is the Fourier transformation. And okay, I'm very sorry. This actually is it should be exponential IKX. So please pardon me my typo. Fx e to the power minus IKX, that's a kernel dx. So that's the Fourier transformation of the function fx, and you get a Fourier transform function fk. Theoretically, it goes from minus infinity to plus infinity. Now this is the numerical form. Now, of course, if I want to calculate this numerically, as you can see, that I have to calculate the integration. Now, as we have seen in the earlier slide, the integration is nothing but summation of areas. So that means I can actually write this as a summation, As you can know, this is something akin to Fourier series, and I have got a summation, and depends on n, and because it's going to minus into plus infinity, so my n is pretty large. Okay, n maybe 10,000, and maybe 10 to the 20, and maybe 10 to the 30, and maybe 10 to the 10. So n should be very large, because I'm actually approximating in finite interval with a very large number of n's. Okay, now suppose I want to calculate this summation. It's a complex summation. As you can see that there's a sine and cosine. If you break it up, it will become sine twice by k n by n. And you just suppose I give this summation to students. I said, students, please carry out this summation. Okay, and by brute force, the naive and brute force way. That means I don't consider anything, just take the summation, and I use my computer and try calculating all these things. You will find that your calculation time goes as an order of n squared. So if n is 10, then your calculation time will go as a 10 squared in hundreds. That means if one calculation take 1 nanosecond, then it will take 100 nanosecond times to calculate things. Assuming that one addition or subtraction takes 1 nanosecond, that's a pretty standard result, 1 nanosecond. Then you will take a 10 nanosecond to calculate 10 number of summation. Now, Cooley and Tuckey, a long time back, they actually use some symmetry property of that expression, that summation. You have a symmetry property. You can, I'm not going to go into details of the symmetry property, but you can have symmetry property, and you can use the symmetry property. Then you can find out by radix 2 algorithm. Actually, that's called bit sensing, some kind of very clever way of arranging things inside a computer. You will find that this order actually comes down to n log n times. Now, n log n doesn't seem to be very, very different from n squared if n is small. But let us take an example if n is large. Now, let us take an example where n is 10 to the power 3, 10 to the 6, and 10 to the 9, respectively. And that's a very usual number. That's not, in Fourier transformation, we actually use these numbers, okay? So now n is 1,000, and 1,000, 1,000, and 1,000, 1,000, 1,000. 1,000, a million, and a billion, okay? Now, what is n squared? It's very simple, 10 to the 6, 10 to the 12, and 10 to the 18. What is n log n? 10 to the 4, 2 into 10 to the 7, 3 into 10 to the 8. It seems that it's not very much different. But let us see how it is actually changing. If you now calculate, if you think that 1 second, one operation take 1 nanosecond, that means if I have a 10 to the 9 number of points, I will take 10 to the 18 nanosecond. How much this is? Can you calculate it out? It's around 31.2 years. 10 to the 18 nanoseconds will come out to be 31.2 years. Now, if you use the same thing by the radix 2 algorithm, then n log n comes out to be 3 into 10 to the 10, and if you calculate this is simply 30 seconds. So that's the power of computation. That means the way you calculate it actually hugely matters your result. How you're going to do that, the way you calculate. I mean, it's it's one of the very, very classic examples in numerical physics. The Cooley-Tuckey algorithm, you can find, everybody use it. That's why it is called FFT, fast Fourier transformation. Now it is a backbone of every filter, backbone of every spectrum analysis, backbone of every image analysis that you do every time your mobile does image analysis, darken the image, background the image, make the instant transparent. These are all done with a Fourier transformation, FFT. So it's so common and so life-changing and so so this is very, very nice examples. So radix 2 algorithms are slightly elaborate and slightly difficult to tell in this class unless you have a purely class on a Fourier transformation. That's why I have just mentioned in the passing that this is the algorithm they have used just to reduce the number from order of the operation from n squared to n log n. Okay, I'm coming to the end of my slide. Just I'll end some fun math. Now it also makes every sense to actually sometimes make the subject, fun out of it. So, and the computer can be a very good example of make fun. I mean, I'm not talking about YouTube. I'm not talking about Netflix. I'm not talking about Amazon Primes. I'm talking about it doing some mathematical function and playing around it. And you might be, nobody knows that you might get hooked. Okay. So consider a complex function. Now, this complex function is a very pretty small function. Z squared, Z is a complex number, e to the power ia. Now, you can take a to the any value, 0 to 2 pi. Okay. It's just a periodicity curve. Okay. Now, you'll ask me that how could I calculate for complex? If you have a Python can calculate complex right away. Okay. I mean, if you put z is equal to x plus iy or 1 plus 2i, then it will give you the fz. Now, this is a recurrence relation. As you can see that fz itself is, if I take z, if I suppose z is equal to 0, then I will get this number depending on a value. Suppose a is equal to 0, then it will be 0.7885. My fz will be 0.7885. Next, I will put the fz into z. That means 7885, I will put in z and calculate fz. And I go on recurrence relation. Then I will get a number of complex. Complex variables are x and y. Suppose I put first 1 plus 0. Then because it's a complex, because it's a ia, okay, then I will get something x plus something iy. Then I put this something x plus iy back into the square and here, then I will get something z plus something x1 plus iy1, and go on and go on. Now, if I plot all these numbers, x1, y1, x2, y2 that I've got from the recurrence relation, if you calculate all the recurrence and keep on plotting this number, then you get this. Okay. Well, of course, the colors are actually automatically chosen to, you can choose the colors depending on the magnitude of the number. And these are false color. And if you keep on playing it, then you can see that this is what you get. And that's really fun. And these are actually known as fractals. And the set which you are getting is actually Zulia sets that you call. Okay. And this is a very fun. So, I remember in my MSc and PhD days, we solved a lot of this equation because it's very fun. It's fun looking, and it also makes people interested to generate very beautiful pattern out of mathematical functions, and they're very integrate, and these are called fractals. I'm not going to talk about fractals, fractional dimensions, but you can do that. Okay, so that's called fractals and Zulia sets, and these are fun. And so that's the end of my slide, end of my talk, and I think I have left 10 minutes time to you for any discussion. Yeah, thank you so much.
Thank you, Professor Madhurya Pratim Bora sir, for your
excellent. Okay, I write Prasad. Yeah.
Okay.
Yeah, tell me.
So we are very much grateful, sir, for sharing your expertise and knowledge with our participant. I am very much sure that our participant get inspired and benefited from your lecture. On behalf of organizing committee, I'd like to extend sincere thanks to you for accepting our invitation and giving us your valuable time for this session.
Okay.
Now
sure.
I allow the participant to interact with our resource person for your query or anything you want to know from Professor Madhurya Pratim Bora sir. Dear participant, please interact.
Thank you all those who have actually said a nice talk. But anyway, this is okay. Thank you, Dr. Luthra and all other people. I suppose. I mean, I don't think there will be any question of as such because this is a very simple talk. I just wanted to.
Can I ask Professor Bora? It was a really interesting and informative talk. I just want to ask, if we go from Simpson 1/3 to Simpson 3/8, we are approximating from a quadratic to a cubic approximation. But the error changes only h to the power 4 and 5, where h to the power 4 or h to the power 5, where h is the step size. So in this case, would you recommend that for students, like which one should be preferable? Because in going from, I think there is a lot difficulty level increased. For teaching purpose, it is all right. But which one would you recommend in order to do?
That's right. No, I think 1/3 is fine because I mean that will solve all the problem. But if somebody is really hell bent on accuracy, one can definitely go 3/8. But 1/3 is fine. I mean that's because that's actually see. First of all, our motive here is to teach the concept behind the method. So once the concept is okay, then student can actually improve upon it. So my point is that instead of actually approximating the straight line, we are approximating with a curve. That's the concept. Now, the way that I have told you, the way that you approximate the curve is a very different one. I may find a different way of approximating the curve, and similarly, Gaussian integration do different way of doing that. So the idea is to give the students, the very simple things, because otherwise it will be overwhelming for them to do, because a lot of things to be done, and also learning Python as such. So I think 1/3 is okay. I mean, you need not go about 3/8, but if somebody wants to do, one can very well do, because there are students who are adventurous and who want to take up more and more. Yeah.
Because what we start with the trapezoidal, and then try to tell them that as we increase the number of steps, it is actually becoming improved. But in that case, computation power is increasing and time is also increasing. And after that, we move on to 1/3. In 1/3, you can do the same task in lesser number of steps. And
Yes,
when we go
that's
to
true.
3/8, sometimes the error in 1/3 is is more as
Yes,
compared to
yes,
3/8.
yes, yes,
So
yes,
that
yes. That's why I
sometimes
said, yeah.
happens.
Yeah. Now that's why I said actually whenever you at the numerical, that's why I said not all the keys actually fit the lock. The numerical analysis is like that's why it is an art of scientific computing, because you'll have to find out the optimum way for your problem at hand. If your problem at hand is solvable by Euler's method, for example, then why do I go by Runge-Kutta? I don't have to go to, because we don't do Runge-Kutta in actually simulation. Because in simulation, when you write a large particle simulation, you'll have to carry out an integration, for example, solving the differential equation, for example, 1,000,000 times per second, 1,000,000 times every state. Now, if I want to do Runge-Kutta there, then I'll be 4,000,000 times I have to do that. That will be completely nonsense. So I will rather use the modified Euler's method to get my results quickly, rather than going on accuracy to do a Runge-Kutta fourth order in a simulation problem. Of course, if you have a standalone problem, you have to be very accurate, solving the trajectory of an orbit. Then, of course, you go by all means go by Runge-Kutta fourth order or even higher. Yeah, it all depends on the problem at the hand. Yeah.
Yeah, that's right. Thank you so much.
You're welcome.
Thank you, sir, for the wonderful talk. Sir,
thank you.
I would ask you one question, sir. Can you slightly elaborate on the Radix 2 algorithm? I have seen the advantage of this.
Radix. Right. Radix 2 algorithm. Let me actually. It's not very. It will not be easy task to do here. Radix 2 algorithm means computers numbers are. I have not gone into that, but everybody, I'm sure you know that computers are stored in bytes. The numbers are stored in bytes. Then these bytes are actually bits. Then bits makes bytes. All of us know that. Now, when you store these things, then you have got the floating point number. You store an argument, a mantissa, and all these things differently, and you combine, ultimately you get a floating point. So that's how the computers are stored. So it's a kind of bit reversal. That means what they have done while storing the number, you change the bit in the computer memory so as to it can represent another number. There's something very clever technique. I mean, like I don't know very details, but the Radix 2 algorithm means that it is something. It's a binary operation, and you have to change the bit level in the bit level in the microprocessor from the computer programming through, of course, because now even in Python also you can change the bits. Even in C also you can say bit level programming. So you change the bit and store the number cleverly in such a way that one number can store several numbers at one time. So it is something related to that. But a Radix 2 algorithm now, of course, it is the fast Fourier transformation is not confined to Radix 2. There's actually different algorithm has come up. They've improved upon it. Even if you are doing image processing, then you must be hearing about the fast Fourier transform from the West, FFTW. Now that has become actually gold standard for fast Fourier transformation. So they are not using Radix 2 algorithm. The Radix 2 algorithm requires that your number is always 2 to the power something. That means either 2 to the power 5, 2 to the power 6, 2 to the power 7, something like that. But now the newer algorithm they do not require radix 2. So you can have any number of number, and your fast Fourier transform will be as fast as they earlier used to be. But I'm sorry that it will be difficult for me to explain at this level, because we need some diagram and an example to explain it actually. So that will itself is a very huge task. Yeah.
I
Right,
understand,
Narayan,
sir.
yeah.
Thank you very much, sir.
Yeah,
Really
welcome.
very interesting. I should definitely look up for it. Thank you, sir. Thank you very much.
You're welcome.
Any more question from participant side?
I don't expect so, because it's a very simple talk.
If no more questions, I'd like to thank once again Professor Bora for answering all the
Okay.
questions from our participant side. And I also
Okay.
thanks all the participants for your active cooperations on this session. I also wish your active cooperations in the next session also. We have one more session with Professor Bora on day 5, 8th January 2001 from 2 to 5 p.m. For the session also, we are looking forward to you, sir. With this,
Yes.
I'm thanking
Yeah.
you all again for this session.
Okay.
Have a great
Yeah.
day.
Thanks very much. Yeah. Yeah. Thanks very much.
So,
Okay. Bye
dear
bye. Yeah.
participants, we are meeting again to
Okay,
at
Prabir,
10.
let me just share my email. Yeah. My email is actually available
Yes,
on the website, but it's mpbora. Thank you, Prabir. Guwahati.ac.in.
okay, sir. I will also share your email address with our
Yes, it's
participants. They can directly interact with you.
okay.
Okay,
Thanks.
thank
Yeah.
you all once again. Have a great day ahead. Dear participants, we'll resume our session at positively 2 p.m. Thank you all.